welcoming everyone to today's CDY session, and we are continuing on our series of multi-messengers, cosmic rays, and gamma rays. And today, it's our pleasure to introduce Dr. Brian Revile. The title of today's talk is The Recurrent Nova RS Ophiuchi and the Galactic CR Connection. So Brian is currently at MPIK in Heidelberg, and he's a well-recognized expert on particle acceleration, cosmic rays, and energetic particle transport. His research focuses primarily in the area of theoretical and laboratory astrophysics. Brian received his PhD from University College Dublin, and then he moved to Max-Planck as a Alexander Humboldt Fellow. But then since then, he's been at the University of Oxford. He's also been at the University of Belfast, and he's currently at MPIK. So let us welcome Brian and get started. And as a reminder, the way we run these is we roughly have 50 minutes of talk and then questions related to Brian's talk, and feel free to use the chat. And then we have a general discussion for the last 15, 20, 30 minutes. So just a note that we will be recording the session and for our YouTube archives. So please mute yourselves if you're not speaking. And thanks a lot, Brian, and looking forward to your talk. Go ahead.
Okay, thanks very much, Rashmi. Oh. So let me. Okay.
Yeah, it looks great.
Okay, thanks. Okay, so thank you very much, Rashmi, for the kind introduction, and thank you for Paolo and Felix and Rashmi again for the invitation.
Right, let me go do it for you.
To talk about the recurrent nova RS Ophiuchi. This was, to my mind, I think one of the most exciting results to come out from the very high energy or imaging atmospheric Cherenkov telescope community in the last 2 years. And I think this is certainly well reflected by the level of interest that people have had, certainly for the publications that have come out following it. I should mention that the reason that I got involved with this specific object, of course, was through my HES affiliation. And so I really need to acknowledge my many colleagues within the HES collaboration, specifically the people who work together on the HES publication on RS Ophiuchi, who are listed here. And of course, all the valuable comments made by the entire HES collaboration. I should, of course, clarify that I am talking here mostly about RS Ophiuchi and with the focuses on the galactic cosmic ray connection. And so I'm not talking as an official spokesperson of the HES collaboration, but really just my own personal opinion. So I'll try to convince you of the experimental bias that I imposed on the HES paper, and maybe convince you that this might be a somewhat physically well-motivated experimental bias. Okay. Okay, so just to clarify then, maybe what I wanted to outline of the talk is to give a summary of the gamma ray detected novae very superficially, and this is not going to be a talk on the physics of novae in general, but really want to make it a talk about RS Ophiuchi and what we can learn from this very exciting event. And so just a quick summary of the previous outbursts and what we learned from those, and then from the present, the most recent outburst in 2021, and what we saw that was new, being the first nova that was detected in the TeV domain. So clearly this is bringing fresh insight onto these exciting transient objects. Okay, so for those of you who are not necessarily familiar with the concept of novae, these are binary systems with a white dwarf and a companion star. The star is overflowing its Roche lobe, and the matter being accreted onto the surface of the white dwarf. And the atmosphere of the white dwarf then eventually starts to heat up until thermonuclear runaway expels the gas from the white dwarf surface, which launches in principle a fast shock moving outward from the white dwarf surface. And they're typically observed as optical transients, with their peak luminosity often approaching or even exceeding the Eddington luminosity of the white dwarf. Interestingly, the galactic nova rate, or theorized galactic nova rate, is on the order of about 50 per year. So if you compare that with the more energetic relatives of supernovae, which occur at a rate of about 3 per century, we're talking here somewhere on the order of about 5 to 10,000, maybe as much as 10,000 per century of novae. But as it happens, the velocities and the ejected mass are so small in comparison that the total energy input is still far, far less. However, they do provide very fascinating environments, or let's say model systems, which should capture in some way, modulo some scaling, a lot of the physics that are relevant to supernova remnants, particularly core collapse supernova remnants. And so, of course, one should take this with a little bit of caution. There are a number of caveats in making direct analogies, but if the questions are well defined in principle, then we can get a lot of additional insight from these events. And being far more frequent means that there is a good chance that we will get favorable conditions at some stage. Okay, so, and by the way, if people have any questions seeking clarity on something, please interrupt, so I don't feel like I'm talking to myself. Okay, so very broadly speaking, novae can be put into two classes, which largely depend on the companion to the white dwarf. So there are the classical novae, which again, the novae are the transient event themselves, falling classical novae where you have a main sequence companion, or embedded novae where you have a much more active companion, basically a red giant or an asymptotic giant branch companion. The main distinction, of course, being that the winds coming from a red giant are far more powerful than coming from a main sequence companion. This, of course, will have a big influence on the shock physics that result post-nova. For the classical nova, the orbits are typically shorter and the orbital separation is closer, as you would expect to get the Roche lobe overflow from a small companion. Whereas for the embedded nova, the stars are bigger and have larger orbital separation, longer periods. Interesting, the ejecta mass is then also slightly larger for classical novae, and again smaller here for the embedded novae. Again, with a large range. This is summarized quite nicely, I think, in this figure. And this is from a review paper on novae by Chomyuk and collaborators. And you can see basically what's happening here. You have the accretion rates proportional to or plotted against the mass of the white dwarf. And based on the accretion rate, you can have effectively a recurrence rate or rate at which you are ejecting your nova. And generally speaking, the amount of mass that is ejected is just simply the product of the time between the nova and the accretion rate. And so very large stars with high accretion rate typically have very high recurrence rate, but eject a relatively small amount of mass. So generally speaking, it was thought that all novae are likely recurrent, but obviously historical records only go back so far. So we're really only seeing these ones up here as recurrent novae. And so for the source of interest for this talk, or Ophiuchi, this was first recorded nova event was in 1898, and then it has had roughly on a 15 to 20 year time scale. Ever since has had a nova event. There are some exceptions here. The dates indicated here in brackets with a question mark. These were the nova itself wasn't detected, but historical records show that there may have been something that was either obscured by the sun and that there was an actual nova event on those years as well. So it seems to be quite regularly accreting matter and spitting out on a 15-20 year time scale. So hopefully something that will be detectable with CTA in its lifetime. Okay, so also from that same review paper, and again, this isn't a talk on novae in general, but this is a very nice and clear timeline of the multi-wavelength picture of novae, specifically classical novae. Here you can see what's more or less happening in the timeline. So you have your accreting white dwarf, some thermonuclear runaway goes on the surface, which causes a UV X-ray flash, which I believe has recently been detected by eROSITA. And then there is this outflow, which is an impulsive outflow, which I think Metzger et al. Were the first to propose that there was a longer-lived, faster outflow that could be launched slightly later. And so the idea here is, and certainly that must apply to classical novae, or something similar must apply to classical novae, is sort of an internal colliding shock scenario. And I think there's a lot of interesting plasma physics that still has to be done on the physics of acceleration and what's happening at these internal shocks. But you can see all the different phases of the non-thermal multi-wavelength emission. But again, what I want to focus on here is on the gamma rays. And certainly in the context of the embedded supernova remnants, where the winds here are much stronger, we know that there are large shocks being produced, powerful shocks being produced, extending up in this direction. And this is going to be the main focus of what I will be focusing on in terms of Ophiuchi. But I'll discuss some other works that people have been exploring. I think it's a very rich data set and a lot more to be explored. Okay, so there has, my last count, there were 17 gamma ray nova detections to date. Again, detected by Fermi. Here's just a handful of them detected. And the thing to note here is that most of them are classical novae. Now, the first one that was detected, B407 Cygni, was, of course, an embedded nova or symbiotic nova. I don't want to get bogged down in nomenclature, but same thing here with had a large red giant companion. Then the natural interpretation was that then this was the shock driven by the nova ejecta propagating into the wind, provided a natural analog to a mini supernova, and could be accounted in the similar type of physics. It was then quickly noticed then, as we started to see many classical novae, that this process wouldn't work and needed an alternative physical model, and that's what was presented on the previous slide. And I encourage everyone to have a look at that review paper. So a few things to note in terms of the Fermi emission. Ophiuchi was clearly the brightest, so it was a rather special event. Of course, it's relatively, or we believe it's relatively close by, which might be later, but then the total energy was significantly higher. The spectrum, and there's a spoiler coming here. So here is the spectrum seen by Fermi. This is nicely plotted in the publication by the MAGIC collaboration on their observations of Ophiuchi. And you can see here the emission from just around the first coincident with the MAGIC observation, so the first 4 days. And then averaged over a longer period of the Fermi observations. And again, you see that the spectrum, it was brighter. The one to compare against, this was the other embedded nova where it was detected. So the blue curve here for V407 Cygni. And also this nova event was observed by Veritas 9 days after the event. And if we, as I'll later show, if you were to make the analogy with the Hess observations, this would probably be already below the detectability. So it could have well been a TeV emitter, and could have been detectable had been possible to observe in the days after, shortly after the nova event. So obviously I've doctored the MAGIC collaborations image here. So let me just put back in their plots. So the data points for their detection, as you can see, connects nice and smoothly into the total Fermi detection over the 4 days of which they took their observations. And I further went and doctored this image, and apologies to MAGIC collaboration members in the audience. We can see here that it's broadly consistent with the measurements on the first night of the Hess observations as well. And so this again was quite convincing evidence of a single population of emitting particles, most likely protons. I think there's almost universal agreement that this is clearly a hadronic accelerator, or Ophiuchi, but not everyone agrees on the single population argument, and so I'll discuss that a little bit later. Okay, so let's take a little dive into the specific binary itself, so our Ophiuchi. So its distance, according to Gaia, the data release 3 or the early data release, is about 2.4 kiloparsec. This remains quite uncertain, and so it could be significantly closer, anywhere from between about 1.5 kiloparsecs out to much further away. So this remains to be determined. But let's say in somewhere in between 1 to 2, 2.5, or 1.5 to 2.5 seems quite reasonable. The orbital period is fairly well constrained, or quite actively constrained, so at several hundred days. The red giant, its mass is also with a certain degree of uncertainty, so somewhere between 0.8 or maybe slightly larger than a solar mass. The white dwarf is generally thought to be very close to the Chandrasekhar limit, and again, this is consistent with the very high recurrence rate and periodic recurrence rate. The mass loss rate of the red giant, the literature has a range of possible numbers, so ranging between 10 to the -8 solar mass to 10 to the -6 solar mass per year. And generally speaking, the wind speed, the asymptotic wind speed from the red giant is thought to be somewhere on the sort of 20 to 40 kilometers per second range. So here on the right, these are 3D smooth particle hydrodynamic simulations by Booth et al. In 2016. So they're really trying to have a look at the global local environment of our Ophiuchi. And so what's plotted here, we have various slices. This is slices through the orbital plane, and this is orthogonal to the orbital plane. And you see here the white contour here plus the Roche lobe with the L1 Lagrangian point here. And you can see directly the accretion or the transfer of mass from the red giant onto the white dwarf here, and the accretion flow around it. The lines plot the velocity field. And then what you can see again, if you zoom out from this, you can see that the orbital precession of the object, of the binary system, drives from the interaction of the wind with the accretion flow, generates these shocks, which tend to merge after about 2 periods, so tend to smooth out over large scales. So seen edge on, in terms of surface density, you see this very thick, dense equatorial plane with this rarefied atmosphere that's falling off essentially as almost 1/r² profile. If you take a direct slice through so this is integrated, taking a direct slice through the binary plane, so orthogonal to the binary plane rather. Sorry, my computer just went dead. Okay, so taking a slice orthogonal to the orbital plane through the center, you see that the mass is essentially accumulating in the equatorial plane with some dense funnel flows here, with this excavated cavity, which is a little bit lower density along the angular momentum axis of the system. And so then the question is, how might this influence the structure of the nova in its expansion? Okay, so this of course will be important for any modeling that one wants to do, particularly in the context of hadronic modeling, but also broadly in the evolution of the ejecta. So here's a rather crude cartoon model. So we have the white dwarf, its red giant companion. It's filling this accretion disk, the density falling off more or less as 1/r². 3D simulations done by Walder et al. In 2008 had a look at just such a system, again trying to replicate the Ophiuchi binary. And so there's a lot of lines going on here, but I think you just want to draw your attention to the black, thick black line and the gray line. So the black line is a line out from the white dwarf going along directly along the symmetry axis. And the gray lines then are going at 30 and 60 degrees. And broadly speaking, what you see is that in the sort of sort of less than 1 AU, where you're really being impacted more or less constant density or very shallow density from the wind, and they accumulated around the equatorial, around the binary plane. You see a very slow decrease in the density until you get out to this region here where you're sort of at the asymptotic wind, and then it falls off more or less somewhere as a 1 over r squared, maybe a little bit steeper depending on which angle you're at. Being slightly higher in these funnel regions, as I showed before, and it's got its minimum directly on the axis, directly above the binary. So what does the magnetic field look like? And so here we have to do a little bit of guesswork. This is very important for the particle transport and subsequent acceleration when we want to launch a shock up through this system.
So Brian,
yes,
quick note. I think we are not seeing your whole slide. I don't know if you're zooming in.
No.
Okay, this is better, but now it's cutting out the bottom and the right-hand side a little.
Yeah,
I don't know.
Same for me.
Okay.
Yep.
Okay, great. Thank you.
Let me just stop the share and try again. Apologies for this. Has that fixed anything?
Yeah, that's better.
Okay.
Yep.
Great. Okay, so where was I? Yes, okay, so for the magnetic field structure, so what we typically will assume is that the wind, of course, is dominated by the red giant, with it effectively acting as a single star, which of course is a rather gross assumption, and one should feel free to attack that assumption, but then please do a detailed MHD simulation. And so then if you are propagating up a long axis according to the Parker steady wind solution from a massive star or from any regular star, pressure-driven star wind, the on-axis you would expect the field to fall off roughly as 1 over r squared, and being preferentially radial. And then as you move out towards the equatorial region, the field should be more azimuthal, toroidal dominated component, and I'll have a slightly falling off closer to 1 over r. So what we expect if the shock is propagating up along here, it behaves more or less like a parallel shock, quasi-parallel shock, which are, we believe, we have a fairly good understanding of how they behave theoretically in terms of particle accelerators. But of course, you're going up through a density gradient and the field is varying. So this is a little bit more complex, but I'll get back to that a little bit later. Okay, so when the shock is launched, or rather the ejecta is launched, it's clearly propagating up through this rather complex, so complex, but let's say non-uniform density structure. And the idea you might expect is that you're sweeping up more mass and going through a denser region in this direction. So you're going slightly slower, or you're decelerating quicker, and whereas you're more freely expanding up along this low density channel. And this broadly seems to be supported by what's seen in the hydro simulation. So again, these are 3D hydro simulations from Wilder et al. And you can see that the velocity, again, colored, the arrows are colored by the velocity, moving about 2,000 kilometers per second, close to the axis, directly above the binary plane, and then moving slightly slower out into the denser equatorial region. So this gives us a clue as to what's happening. So how does that match with observations that were taken around 2006? The early observational data was nicely summarized in this work by Tatishev and Hernandez, which is also a very interesting paper, and the first, to my knowledge, that really tried to address the possibility for gamma ray emission from novae. And so what they took, basically accumulated all the observational data at the time based on the infrared, full width, zero intensity, approximation for the shock velocity, and then also from the X-ray data relating to the assumed temperature fits. What the general consensus was that the shock velocity is quite consistent with more or less a t to the minus half, or the shock radius expanding as t to the half, which was what you would more or less expect either for a non-radiative shock. So this is just an energy conserving setup solution going into a 1/r profile, which again is not really what's seen from the hydro simulations, or from a radiative shock going into or 1/r² types scenario. Both of these are a little bit hard to match with the theoretical models, broadly speaking. I've added just details here for consistency. But if you think about it, what's more likely to be happening, as I showed on the previous slide, is that the outflow is going to be something that's more like, or the global shock structure is something more like a dumbbell or type profile. This was the profile that was suggested here by Ribeiro, and also earlier work by Bode et al. And so what you could be dominated here by is the emission that you're really seeing from the parts of the shock that are moving quite slowly and expanding out into more dense medium. So it could be dominating this. And this is generally supported by the fact that we see, or let's say the strong evidence, that the shock is expanding in the bipolar, again in the plane orthogonal to the, or in the direction orthogonal to the binary plane, very fast and consistently for many thousands of days. So here were Hubble images at 155 days and 450 days, roughly. So this is a synthetic image, and this is a deconvolved optical image here and here. And they can make the angular expansion measurements. Now, of course, the angular expansion, you convert it into an actual velocity measurement. We need an accurate guess of the distance, but again, if it's somewhere in the range of 1.5 to 2.5, it's not a terrible difference. And it implies that the flow, even extending out to 2011, was sustained at a velocity of several thousand kilometers per second. Okay, so clearly indicating that the results from the very early measurements were not the full picture. This lends some comfort for at least the simple models, where you can probably safely get away with applying fairly high, reasonably consistent, constant shock velocity. Okay, so this brings us up to the present. So on August 8th, the year before last, 2021, the nova was observed by a number of amateur astronomers. And I encourage people to have a look at the very interesting and entertaining dialogue going on in the comments section, this link here, challenging one another's claims. But clearly this was a very bright event, and it was also detected by Fermi very, very quickly. It was significant detection, and so most IACTs now have a clear, well-defined transient nova follow-up program. So Hess and Magic have discussed this at length, and of course naturally followed up this very, very interesting event. Just to show, here is again the optical flash, and so this is what the accumulated data for the first 5 days from Hess. And you can clearly see a very significant detection. In fact, the detection was above 5 sigma on every night for the first 5 nights that the Hess was observing. Okay, so what did the Hess actually observe? So I did a sneak peek at the beginning, but let's do a bit of a more deep dive into what the gamma ray observations are telling us. So the flux was again here, so the flux, I've got the Fermi flux rescaled to sort of be on the same level as the Hess data, so factor 3 orders of magnitude reduction. What we're seeing here is the integrated flux from Fermi from 60 MeV to 500 GeV, and the Hess flux from 250 GeV to 2.5 GeV. What we see is that the Fermi flux in that band peaked more or less approximately a day after the peak in the optical. So we find T0 here as the peak of the optical emission, and the Fermi flux peaked about a day after, the Hess flux peaking slightly a day or 2 days slightly after. While at first sight this might seem strange, when you look at the actual spectra, this becomes a little bit self-evident as to why this in fact was the case. The subsequent decay timescales are more or less comparable, effectively going as t to the minus 1.3, 1.4. Within errors, they're consistent with each other. And you point out that the emission was detected with at least out to about 3 sigma, out to several weeks, more than 3 weeks after the peak brightness. Okay, so again, I apologize for doctoring magic collaboration images, but I wanted to sort of compare like with like and be as broad as possible. So here is the Hess spectra observed on 2 different nights. So on night 1 and night 5. So first night after the peak brightness, and then on the 4th night after, 5th night rather. And so what you see is this general trend that the Fermi band, so the low energy gamma rays, the flux is generally decreasing, while the overall spectrum SED is broadening. This could be interpreted in a number of ways. The way that we in the Hess collaboration had interpreted this was generally just populating the high energy tail of the distribution, right? So that it was somehow reflecting the combination of time-dependent acceleration, filling the high energy tail, but then also in terms of mixing and filling the cooling zone where you might be, for example, interacting with the dense material of the ejecta. I think this similar type or very similar interpretation was applied by the MAGIC collaboration. And you see a similar type behavior from their data and their model fits, that you see this reduction in the total flux, but a broadening which allows the spectrum to extend out to higher energies. And I can come back to this a little bit later. One thing to note again is this nice fulcrum point, which appears at about 100 GeV in both models. So some crossover. Okay, sorry. So the question that we might ask is, and then bringing us back to this cosmic ray connection, what is telling us about galactic cosmic rays is, of course, what can we learn about these observations to test maximum energies in supernova remnants? People have heard numerous talks, not least Frank's talk just a fortnight ago on the challenges to particle acceleration in supernova remnants. So the main challenge for cosmic ray theorists is how do we account for cosmic rays up to the knee in the spectrum? And while we're only really just getting to just above a TV for these observations here, in principle, if we scaled up, would they give us additional insight into what's happening in supernova remnants? So we have to do a little bit of a digression into the maximum energies and what are the predictions, how they compare to these observations, and if we can extrapolate them to supernovae. So this is probably familiar to most people in the audience, but just a quick reminder. I'm not going to delve too much into this. So the simplest limit that one can really place is this very back of the envelope. The maximum energy is of any particle or any system is effectively the work done on a particle by the electric field. This was pointed out by Hillis back in 1981. And if you make the ideal MHD assumption, which is, of course, a very good approximation on the scales of a supernova remnant, for example, then the electric field is effectively just the velocity times the magnetic field, and the total path length is going to be on the order of the system size. So you can say that this would be the maximum energy that would be, or the energy that would be achieved if a particle crossed this entire system, seeing effectively the mean electric field of the system, where beta and B are characteristic velocity and magnetic fields of that system. So for a supernova remnant, this system could be maybe a few parsecs across. Shock velocities are typically on the order of about 1% of the speed of light. The open question, of course, is the magnetic field. I'll get back to that. an alternative way of thinking about this, which is tied more to a physical model, is that approach of Legage-Cesarski and others. And what they had a look at was to consider the limit of magnetized transport. By that I mean the Bohm diffusion. This effectively corresponds to the diffusive transport that you get when the mean free path is equal to the gyro radius of the particle. So this is a magnetized limit. Of course, if the mean free path were less than the gyro radius of the particle, then it wouldn't make any sense to talk about gyro motion at all. And then this expression, you need to have a different approach. But what we typically then do is assume we have some sort of measurement of the magnetic field, scales as the energy, and then this determines effectively how well the particle is confined to the shock transition. And of course, the more times the particle can cross the shock, the higher its energy. This is represented by the acceleration time, which is well known to scale as the diffusion coefficient. So smaller diffusion coefficient, shorter acceleration time, and inversely with the shock velocity squared. So faster shock, faster accelerator. So if we equate this acceleration rate in the optimal condition of Bohm, the Bohm limit, we can find an expression for the maximum energy because the energy is appearing here. And we find that gives this expression here, and making the obvious observation that the term here in brackets is no different than an expression for, or is a proxy for the system size. Then we see that the maximum energy very much very closely approaches the Hillis limit. This is perhaps not surprising. If you have the optimal scattering rate, then in principle you get up to the optimal maximum energy. Okay, so this is sort of an efficiency measurement. So if we just take some numerical numbers, plug them in for a supernova remnant, we get to the age-old problem of the Legage-Cesarski limit. That was where it was first introduced. That supernova remnants have a bit of a problem if we take sort of typical values. So we don't get to the knee. So at 10 to the 15 electron volts, we get to within an order of magnitude, but just getting that last factor of 10 seems to be problematic. What has become now commonplace, and you've probably heard this now multiple times, that the choice that we choose for the magnetic field here is somewhat contentious. We know from, or let's say there's very compelling evidence from observations of supernova remnants, that these fine structures that we see in X-ray around most supernova remnants are clear evidence of very strong magnetic fields. And so the magnetic field value that you should be choosing here could be significantly larger. What value you choose, of course, is not clear, because it could be the total magnetic field or the RMS magnetic field. It could be the magnetic field that is effectively the Fourier components close to, or the energy density in Fourier components reasonably close to the gyro radius, which effectively determine the scattering rate. So the number that goes in here is less clear. So the question is, can NOVA observations give us additional insight into this? So let's have a look at what the model might suggest for our Ophiuchi. So if we again follow our simple Parker-Wind solution, again assuming the shock was propagating this bipolar outflow going up along the axis, the magnetic field will be falling off approximately as the shock radius squared, and therefore we can substitute this into the Hillis limit or Legage-Cesarski limit likewise. And if we make the assumption that the fields at the base of where the wind is launched was about half an AU with the 1 Gauss magnetic field, we would get an expression here for the maximum energy, which is close to 10 TeV. And you would think, oh, that this is absolutely fine. One has to be a little bit careful here, because if we take the shock velocity at 5,000 kilometers per second, already at the time of the peak of the Hess emission, the shock will have moved 10 AU. And so this would have fallen down by an order of magnitude. And so you'd be down producing TeV, maybe protons, which would be difficult to account for PeV gamma rays. Also, the magnetic field value here is possibly optimistic. One could play around with these things. You just need to make sure that your wind at the launch site is super alphenic at the base of the wind. So that restricts this somewhat. But irrespective of this, it seems that already we saw that to get Hillis, to achieve the Hillis limit, we need to be at the maximum possible scattering rate, which means that we have to self-generate scattering fields, or if we really are in this steep falling off condition, with the field falling off as 1/r², then we have to have some sort of magnetic field amplification. And again, there is strong evidence that magnetic field amplification occurs in a number of sources, and it seems clear that it's also occurring in Ophiuchi. Okay, so quick digression into how that might be occurring, and I'm not going to delve too much into the details. We've heard about this before as well. The simplest picture that we can sort of to motivate it, in order to get the particles accelerating, they have to be confined. So you preferentially want to amplify magnetic fields ahead of the shock. Behind the shock is nice, but without the significant field amplification ahead of the shock, particles will just free stream off to infinity. In the steady state picture, you normally have this profile where you have a extended precursor extending ahead of the shock. So in the shock frame, this is driving or represents a current that's propagating into the upstream, and then the incoming background medium is flowing in this direction here. So if we make the assumption of ideal MHD, we know that the electric field is U cross B, and then from Ampere's law, we know that the cosmic rays, which are just doing whatever they're doing, and then the external magnetic field has some particular curl, which is again unrelated, or before the shock arrives, it doesn't really know what that should be. And so when the cosmic rays penetrate through, these two terms are not in balance, and so the MHD background fluid has to respond in some way, called this return current. And very simply, if on scales much less than the cosmic ray gyro radius, cosmic rays are rigid and they don't care about these small scale fluctuations, but the return current is highly magnetized. So this current is magnetized, and this leads to an uncompensated current which drives a runaway instability. So this was first investigated by Tony Bell back in 2004. And as you can see, these simulations here where the fields are growing on small scales. So I should point out the scale here would be initially on of the field growth is very much less than the gyro radius of the cosmic rays that are driving it. But as you let the simulations run on, it very quickly extends or cascades to larger length scales, more or less to the size of the box. One can ask if this is some artifact of a numerical artifact, and in some sense the long-term behavior is, but just some simulations that I had done many years ago, where we extended this by the simulation box by a factor of about 5, and you can see here this is more or less contemporaneous with this figure here, and then a subsequent time where you see these expanding filaments, strong magnetic field generation, and they more or less drive into each other and almost explosively transfer into this sort of stage here. So when the nonlinear stage, or when the fields basically start to become nonlinear, they very rapidly transfer to larger scales. And so this seems to be a natural way to amplify the magnetic fields to a very large level and on a sufficient scale and energy density. So can we construct a self-consistent picture of this? So this is my current thinking of it. Other people might have a different thinking. So this was a model proposed by Tony Bell and our colleagues back in 2013. And so the idea is we know the linear growth rate. And so the linear growth rate more or less depends on the current provided by the cosmic rays. So it's directly proportional to the cosmic ray current. Here, this tells you more or less the time scale on which it's growing. And so if you imagine a fluid element that's very far upstream, it just starts to see at some point cosmic rays passing through it in the frame of the shock, then it's moving in towards the shock, and the fields are growing in that fluid cell as it's moving in towards the shock. And at some point, the fields are highly nonlinear and then confine particles within this region here. And so if we sort of make a rough estimate that this is somewhere on the order of 5 to 10 growth times at the fastest growth rate, or 5 to 10 e-folding times, so to speak, one can then invert this based on the simple confinement condition that we want several growth times. Growth times depend on the escape current, and if the escape current is dominated by the maximum energy cosmic rays, then we can invert that and find an expression for the maximum energy. Sorry, T here is epsilon here. This seems like it's a very useful expression. First thing to notice is that it doesn't depend on the magnetic field, but that's of course is more or less hidden in this confinement condition. But this result in fact holds up quite well with observations. So if we take typical age of supernova remnants, shock velocities, assuming reasonable efficiency of about 10% and gas densities, we see that the implied maximum energies are broadly consistent with where the maximum gamma ray energies are seen from most of these remnants. Even remnants, which should point out like Ca, where we know there is strong magnetic field amplification. So if we were to naively put in 100 microgauss into the Hillis limit, we would have predicted a much higher energy. And so what this is showing is that it's just simply not on the right scale. So what does this tell us about our Ophiuchi? Well, it's a slightly different system here. Now we're considering systems where we're not going into a constant density, and the shock velocity might necessarily be constant, but again, we'll try to keep that as not worry too much about that. But we can revise these estimates. This was done in the 2013 paper. We can revise these estimates allowing for a radial dependence on the density. And so for a wind type solution, one can work out a similar maximum energy argument. And so we see that it's slightly more favorable. So even though the time might be much smaller, the shock velocity can be larger and the density can be much larger. And so what seems to happen is that what's the dominant effect for the maximum energy is the mass loss rate. We need fairly slow wind velocities. So this determines effectively the mass per unit length that's been swept up by the shock, and very high shock velocities. Okay, so if the conditions are right, in principle, we can push this slightly beyond a PeV, but it seems to be quite difficult to get much beyond a PeV. And there we might need to look for other sources. And we heard a little bit from Stefano Ophiuchi a few weeks ago about that. Okay, so let's take now the numbers that might apply for our Ophiuchi. So now compared to the core collapse scenario here, where we have very high mass loss rates, we know the mass loss rates are much lower for the wind of the red giant companion and our Ophiuchi. So it's more like 10 to the minus 7. If we take these as rough values, we see that the maximum energy is significantly less, but exactly in the ballpark where we expect it to be, or at least consistent with the TeV observations. So this at least does not contradict our model predictions for the maximum energy, and in some ways support it. Okay, so I'm going to finish up with some examples of the different models that people have used to try and interpret the data. So what we want to more or less fit is the gamma ray data here. So really looking at the Fermi flux and the TeV, or the very high energy gamma ray flux. Obviously Hess was following Hess data, and then other people have had a look at the MAGIC data and the combined data. So here were the two models presented in the original discovery papers. So on the left, we have the Hess collaboration results. So just mention briefly what goes in. I'm going to only focus on the hadronic model, not worry too much about the leptonic model, but if people have questions about that, I can address them. So the model that was adopted by the Hess collaboration, and this was largely Mitya Kangulian's hard work. And so what we saw here, the model essentially takes a fixed ejecta piston and propagates this into the wind, taking into account the slight offset between the red giant and the white dwarf. This allows for time variable density conditions and gradient, which allows again for slightly time dependent maximum energy and shock velocity. But the shape of the injection and the overall profiles were generally tried to keep fixed, right? So we were trying to develop a model which had as few free parameters as possible, but of course there was a certain amount of time dependence involved due to the, let's say, sophistication of the approach, but very few free parameters. And overall, you can see that the results provide a reasonable good fit. You can see that the overall flux in the Fermi band is falling each night, consistent with the data, and we get a reasonably good fit to the Hess data. You could argue that could get a slightly harder spectrum out here at later times. This could have been, of course, incorporated by including some time dependence in the shape of the injection spectrum. But again, we're trying to keep it a simple model. This is more or less confirmed then by, or at least supported by the MAGIC analysis. So here they were just doing fits for each individual night, and they were allowing for the shape of the spectrum, again the emitting spectrum, and the position of the cutoff to vary with the different nights. So this is day 1, day 2, day 3, day 4. And you can clearly see the trend is for an overall flux reduction, similar to what we saw in the Hess analysis, and a spectral softening, and an increase in the maximum energy year time. Okay, so that's again this broadening that we see. And obviously then being the multi-messenger section, the MAGIC collaboration also had a consideration of the neutrino flux. But there's no chance of detecting any neutrinos, or there was none. Here's ice cube upper limits. Okay, so I mean, a big success, and what is very nice to see is that other groups outside of the collaborations have jumped on this data and started developing their own models. So this is really good that the conversation has started. And so the group coming from China had a look at doing, again, hadronic models, allowing for various time-dependent evolution of the shock and density profiles and the various considerations. And they again find a fairly reasonable single-zone time-dependent model, which is broadly consistent with the Fermi data. Does pretty good fit at early times, and maybe slightly off at later times for the Hess data. And you can also see they've also tried to incorporate the MAGIC data as well here, so you see fits quite smoothly in between. Another very interesting approach that's also been taken, and quite an alternative approach, I would say, in some sense, recently appeared on the archive, or like last year, by Rebecca Deasing and collaborators. And here they make a different approach, where they assume that there are two shocks, or two zones, so to speak, with slightly different conditions. So basically a slightly slower shock, which has a similar profile but a slightly larger initial density. And so that region is effectively accounting for the Fermi data, and this matches more or less smoothly into the very high energy data. Here they only consider the Hess data, and you can see that you can produce a reasonably good fit for these 2 nights that are observed, and broadly speaking match the light curves very well. So this is, of course, another interesting approach, and something that I think warrants a lot more follow-up. Okay, so I think that has me more or less at coming to my conclusions. I think that the IACT instruments are bringing a very unique perspective on novae. Certainly strongly constrain the theoretical models, and it will be very nice to see, similar to what was done in the wake of the 2006 burst, to have a look at how we can compare this in a very much a multidimensional MHD type scenario, including our understanding of particle acceleration, or improved understanding of particle acceleration since then, and various plasma processes, particularly related to nonlinear magnetic field amplification, how we can merge these to really enhance our understanding of these complex systems. One obvious point is that if ORS Ophiuchi is typical of embedded novae, then CTA will have many opportunities to observe similar sources, And with its improved sensitivity and energy range will tell us a lot more, hopefully with better visibility conditions than those that plagued the observational campaigns of Hess and Magic, with the moonlight and whatnot that affected our taking data. One thing to point out is that despite the much larger rate of events, the total energy input from novae is dwarfed by that from supernovae. Nevertheless, the larger rates provide many opportunities to explore the non-thermal processes, as long as we have well-defined questions, and certainly occurring at or near the shocks of the core collapse supernovae and their remnants. An interesting aside here, in the paper by Diesing et al., they emphasize caution on making a direct comparison between novae and core collapse supernovae, essentially due to these multiple shock type scenario that they consider. And I certainly would share these caveats, consideration of these caveats. But of course, the thing to remember is that core collapse supernova remnants are very often going off in binary systems as well. And so then one can flip that and say, well, maybe if there is something else happening, that there are these multiple shocks, it might somehow also be hinted at from the novae and give us insight into what's happening in binary systems where core collapse supernovae are taking place. Okay, so I think that brings me to my conclusions. New gamma ray discoveries are changing how we think about cosmic ray origin problem. I think the origin of cosmic rays much greater than PV is still unclear. I could have spoken at length about this, but preferred leave that maybe to another seminar. But encourage people to have a look at recent papers by Thibaut Vieux et al. The plasma physics of cosmic rays and their self-generating fields are broadly consistent with these nova observations, which hints that we're possibly doing something right. But I think people should still explore this further. A lot more work needs to be done, particularly in bridging the multi-scale aspects, which again is something where observations are really instructive, and of course simulations are improving all the time, and so we're constantly seeking inspiration from these. I hope I've convinced you that TV novae are a fascinating platform to test our models of particle acceleration, magnetic field amplification in general, but also that should go both ways. And so we should be able to reverse engineer our models to get additional insight into the winds of these binary stars, and from red giant stars in general, which are again not so completely understood. So hopefully future observations will provide additional insights, but I think much work needs to be done before we can say we understand the non-thermal physics of Ophiuchi. And so hopefully this is just the start of the conversation, and then there will be many more detailed multi-dimensional studies attempting to improve the self-consistency will appear in the coming months and years. So thank you for your attention, and then hopefully we can have a useful conversation now. So I don't know who my chair is.
Yeah, Paulo should know.
Me, okay, or Felix too. Yeah. Yeah. I guess we'll take over and we'll open it up to, well, first, any specific questions about Ophiuchi, and then we might open up more generally to MHD particle acceleration and field application. So I see Evgeny there, so go ahead if you want, ask your question.
Actually, I have two questions.
Okay. Yeah.
One is, what about the maximum energy of accelerated protons? If you just take Hiller's limit, it seems that it doesn't grow with time. So why should this maximum energy grow in time? What's the reason for that?
So hang on, maybe let me go back. I assume you're talking about, because here it would be decreasing in time, but within this solution, is this what you're referring to, Evgeny?
We're not seeing anything, Brian, if you're trying to share.
Yeah, yes, I only see your face, sorry.
Apologies. Okay, sorry. So you see, there we go. So we see this expression here.
Yeah, exactly.
Okay, so the way that I was thinking, or the picture that I have in my mind, right? So you have this situation where to generate the fields, the only thing that really matters is the amount of charge that is passed through a given fluid cell. Okay, so that's effectively what's happening, is the integral of the escaping flux with time as a fluid cell is advecting in towards the shock. So it turns out that because in a 1/r² wind profile, you're injecting a lot of particles at early times, and they're escaping then. So there's a high energy flux, but it's also then diluting as it's expanding out, as again diluting as 1/r². So the total flux that's passing through a given fluid element per unit area is more or less constant as it advects in. So by the time they are in a position to confine, then it more or less saturates. Okay, so this accounts for why this term here and this term here are effectively in balance. Okay, so there's no time appearing here, and then the density is just represented by this constant loss length. Now, why does that increase the maximum energy? I don't think it's an actual increase in the maximum energy. I think you're just time dependent populating the tail of the distribution. So this is more or less that you can accelerate particles up to that energy, but and you certainly don't get very far beyond it, but it takes a finite amount of time both to populate that tail of the spectrum, but then also to get it mixed in. Why we see it in the gamma rays, the amount of time it takes to mix in with the ejecta. So all of these single zone models, of course, have no treatment for the inhomogeneous distribution of the target material within the ejecta. And so this again will reflect in a gradual filling up of the flux of TV to TV photons. At least that's the way that I'm thinking of it.
But the acceleration timescale is the same as the expansion timescale. They're not different.
Yes.
And that means you cannot say that the particles need some time to be accelerated unless you grow the acceleration limit in time. But if it's not, then you reach this limit essentially early in time. It shouldn't take longer than the expansion.
Well, it depends on. I mean, again, you're filling still your cooling zone model, right? And so, of course, this is some sort of steady approximation, which take into account. And so that was simply the way that I'm thinking of it. But you're right. I mean, this needs clearly in the case of Ophiuchi, it's a very complex environment with different density shells going on. This is why I think I was quite eager to see people pursuing the approach that Rebecca's following, where you consider different densities, and then applying what we think is happening in the magnetic field amplification in the different latitudes, so to speak.
Okay, yes, I see. And the second question is completely different. Think of electrons, not protons. They also should be accelerated in the same way, more or less. And if I'm not mistaken, I just did it in the course of your talk. If I'm not mistaken, they can also reach TV energies more or less. So why people do not consider electrons' contribution to the gamma ray emission?
Yeah, so in the Hess paper we did. So you still need to have, in theory, some additional element of magnetic field amplification, but then the maximum energy is slightly lower. I think you're about right. I think you have to account, the maximum energy, you have to be a little bit limited by the inverse Compton losses is dominated, but I think Klein-Ashina works a little bit in your favor. And so we did consider a leptonic model, and also the Magic Collaboration considered a leptonic model. It's in principle possible. The reason we preferred the hadronic model was that the injection efficiency needed to be incredibly high, so even higher than it is in Cas A. So we needed to have roughly a few percent of the total jet luminosity or shock luminosity had to be converted into electrons. And so this was the reason for disfavoring it. But we do have fits for this in the Hess paper. So it is just about possible. And we did have to assume in the model that the the spectrum was rather shallow in terms of its rollover, so that it was extending out to quite large energies beyond the cutoff. But it does also,
Okay.
I mean, broadly speaking, it's perfectly, I mean, if you don't take into account the general consensus that the electron acceleration should be much less than 1%, which is more or less what comes out of from the kinetic simulations. If you disregard this and just remain agnostic and say, can you fit it with a leptonic model? Then the answer is yes, you can, with tweaking the parameters.
Okay, so essentially you just need a few times more energy than standardly assumed, something like this. I see. Okay.
And again, a rather shallow turnover. But again, there are models, and maybe Felix will probably mention this now, that there are models which suggest that leptonic models should have a more gradual rollover when they're loss limited.
Thank you.
Okay, maybe we'll go to the next one. Just before that, one question for me. If it's a hadronic model, but there's always electron acceleration, is there a hybrid sort of feature, maybe in X-rays or something, the electrons dominate, or is there any hint of that?
This will be something, so we didn't look at it at the time. There are multiple X-ray papers that now have appeared. I would hope that people are revisiting this. Certainly, I know that the LST also presented preliminary observations at the last Gamma symposium in Barcelona, and so maybe in their preparation of that, they might have a look at looking also at leptonic emission from the X-rays. We did have a look, so Mitya did have a look at doing a hybrid model for the hadronic emission, or basically doing a leptohadronic model for this. The general consensus within the Hess collaboration was to keep it simple and just have as few free parameters and look at them each individually. So that's what we did. But clearly there's, I mean, this is one thing that in Diesing et al, they do a better fit of fitting these last few data points. We had proposed then maybe that the leptonic model could fit some of these and the hadronic up here, or vice versa. One can play around with these parameters. But yeah, looking at the X-rays, hopefully something that will be done for the LST paper, or hopefully many other groups, I hope, will using the full data set.
Yeah, it's pretty cool. All right. The next question, I think in order, was Frank. Do you want to ask your question? Frank Shen?
Yes. Can you go back to the page 19? Yes, in this formula, the maximum energy is very sensitive to the shock velocity. Is a square relation, and we know the Hess peak is 2 days later than the Fermi's peak. And generally speaking, the shock in the stellar wind is decelerating. Can we exclude this model because it's generally decelerating, but the maximum energy is increasing? It sounds contradictory. Can we exclude it, or we have other, or this model has any advantages?
Okay, so I mean that was kind of the point that I was making here. Sorry, could you mute because I'm getting feedback? So while it's true that there is strong evidence that there is deceleration of various components, there's also quite convincing evidence that the shock, at least the one that we were considering in the Hess paper. So in the Hess paper, we were exclusively considering the shock moving up on axis, and in that case, there's no evidence that the deceleration is very, very low. The shock velocity would have to maintain, or at least there's a feature that's moving at a velocity that, of course, it depends on your assumption of the distance, but it's moving at several thousand kilometers per second, and it's doing that for several years. So it would be certainly true that if this was the only shock that was where we were looking at the acceleration, we would expect the maximum energy to be decreasing quite rapidly, unless there was some playing around with the magnetic field. Interestingly, if we take the adiabatic solution, or the Sedok-Taylor solution for a 1/r² wind profile, if the magnetic field stays constant, so if you can sustain magnetic field amplification, the maximum energy actually doesn't decrease in the Hillis limit, because the combination of the system size and the shock velocity still increases in time, albeit weakly. But I don't think there's any contradiction. Just that what we need is people to do full 3D MHD simulations, somehow incorporating the global structure and self-generated fields and particle acceleration.
Oh, okay, I see. Thank you.
All right, thanks. So I guess the next question is from Felix. You want?
Yeah, thanks, Paul. So, Brian, again, back to the question about electrons. So yes, I think it's, we know that both electrons, protons in principle could explain. And now the question is an interesting question. What will be then the ratio we need in protons, total energy to total energy of electrons? Like, you know, in supernova remnants, there's a bit not a bit strange situation that when we explain by protons, we need as standard one is typically 10 to 50 arc in protons, while in electrons is sufficient just 10 to 46 or even 47 arc total in electrons. So ratio is more than 10 to 3, while we have in cosmic rays 2 orders of magnitude this difference. Now it's so this, I think only supernova remnants, if I'm correct, only for Casei is more or less nominal ratio is 100 protons to electrons, but for all other supernova remnants is more than 3 orders of magnitude this difference. So what is in this case actually?
Yeah, so it was a factor of order unity actually. So the leptonic,
so one.
It was
one.
Let's say to get the hadronic model here had I think an efficiency of on the order of about 10%. You know, so typical like we expect from supernova remnants.
Mechanical, yeah.
But for electrons, we would have needed about 2%. So factor of 5 difference only.
That is very interesting actually, because when we have to take this analogy of supernova remnants shocks, so that is quite different than in supernova remnants. Although I think in Casei it could be something like
Casei, yes. Casei is
an exception. For all other gamma ray emitting supernova remnants is more than 3 orders of magnitude.
Yeah.
Okay.
So just to clarify, and I think also Magic came to the same conclusions, that it was the high efficiency that more or less disfavored a leptonic model for it. I mean, I think it's almost certainly I would be shocked if there wasn't some electrons being accelerated there and non-thermal electrons. And so
yeah, okay, this is a leptonic. It's a question of the test. I mean, that was, but this ratio is more objective stuff, so that is interesting. Yeah, that is much closer. So it could be related to the injection, different conditions of injection.
Yeah, and I think, I don't know if Damiano's online or other people. I mean, now the people who are doing these particle and cell simulations, for better or worse, tend to see compatible numbers. I know there's a number of papers where you see the ratio of the energy going into electrons to protons is typically a factor of 100 or so.
Where?
For quasi-parallel shocks. Sorry?
In supernova remnants or in general?
These are, just simple idealized shock simulations. So they're just done in dimensionless parameters. So it will be a Mach 30, 40, 50 shock or, with mass ratio much larger than unity.
You know, but that's interesting. I mean, people like this 100 and they try to get to 100. But in fact, it's not 100 in supernova remnants. So that was my comment. So somehow, okay, thanks.
Yeah, no. So I mean, I think again what Paolo said is a good idea, and hopefully with future papers, people will try to have a look at a real multi-wavelength model and try to find hints of this, because I think that the magnetic field should be reasonably well constrained. If we believe it's Hillis maximum energy, then we know the size, we know the velocity, so we should have a fairly good estimate of the magnetic field, and that should more or less give us a clue as to what we might expect in terms of brightness.
Okay. Any other questions around there? I can come up with some myself, but anybody else have some thoughts? If not, I'll say my, oh, Valenti, okay, you raised your hand. Yep, go ahead. Yep.
Yep, can you hear me?
I can hear you, yeah.
Thank you. Thanks, Brian. It was a nice and clear talk. I have a kind of very general question, because I was thinking while you were discussing about this ratio between protons and electrons, then in other binary systems with other, let's say, type of ingredients, like you have two massive stars, but you may have also a massive star or a low mass star and a compact object. In the case of binary massive stars, massive star binaries, you have, as far as I remember, relatively low non-thermal budgets. Like, for instance, recently we published a paper with a hint of non-thermal emission from a quite powerful binary system, and there it was something like in electrons, like maybe 10⁻³ of the total energy was going to relativistic electrons. On the other hand, we have these gamma ray binaries with a compact object, and there the most likely explanation is leptonic emission, and you have efficiencies like luminosity budget in non-thermal particles is like maybe 10%, or it could be even more of the available energy or luminosity budget. So you have, of course, you have different kind of ingredients in these systems, because all these binaries are quite different. But well, it's interesting to see that you have systems which look more like supernova remnants, while others are more like pulsar wind nebulae. So I don't know, it's a comment, but I would like to hear your thoughts about this.
Yeah, well, thank you there. I was expecting some comments. Hopefully I did the magic collaboration justice.
Well, I'm not in magic, but anyway.
You're not in magic anymore.
I can be associated to them, it's fine.
Valenti's anti-magic.
I'm not anti-magic.
So yeah, so I think broadly speaking, I think those numbers tend to add up, right? So what the numbers you said there for, and I think this was on the APEP, wasn't it?
Yeah, right.
Okay, yeah, see.
Yeah,
Came up on the radar. So those numbers are again are broadly consistent with the numbers that Felix was saying. So this sort of 10% of the luminosity is going into hadronic material, and then about 1% of that, so 10⁻³ of the total, going into electrons. This I think is, yeah, more or less makes sense, and it is broadly consistent. Why I think Felix makes the relevant point that Cassé is an outlier, and why is not clear, but certainly a fascinating source. I also would tend to, I think the last few years, as we've really seen, certainly with Hawk and Lasso, that pulsars and pulsar wind nebula are a constant source of amazement, and remarkably efficient engines, accelerating particles very effectively and very efficiently, and up to very, very high energies. And so I would suspect in these compact binaries, then you're being dominated really by the physics of the winds. But maybe it's some interplay is ongoing. I know we've briefly discussed this, but I think this is also something that warrants more discussion, certainly in the context of cosmic rays, right? Because if you can get hadronic material into the winds of the compact object, then in principle you could start to get very interesting physics.
Yeah, actually, well, hopefully we will discuss this in person soon. But in any case, the thing is precisely that. So where you have the accelerator in binary systems, where you have a compact object and you may have relativistic jet or a relativistic wind, because there you have also the stellar material. You could have the acceleration region contaminated to some extent by hadrons, by baryons, but not too much. So you can still operate in this very efficient leptonic way, and then you can add some amount of protons and nuclei to the mixture. But indeed, it looks like relativistic, let's say relativistic outflow binaries. They tend to be more efficient. They seem to be more efficient leptonic accelerators. And then you have these non-relativistic ones, which are more akin to supernova remnants.
Valentin, I would agree. Sorry, interrupt you.
No, please go ahead, Felix.
Yeah, I agree with you. I mean, with your comment, but regarding this ratio, for protons, it depends strongly on the density. So if we think that we can estimate density in supernova remnants or in this system, is okay. But do you think you could have a quite good accuracy for density to make a statement regarding the total energetic in protons?
Is it a question to me? In which systems?
No, to you. I mean, for binary systems.
Well, what I'm saying is, in these systems, the spectra, the behavior in general, and the densities for targets favor leptonic processes. But you cannot discard that there is still some component of hadrons being accelerated there, but they are not seen. I think they are not seen in the radiation, but they could contribute potentially to some level to the cosmic rays.
Yeah, exactly. This is my point. I mean, if you don't know if density is low, I mean, protons could be there with huge amount, but we don't see them because there is no sufficient target.
Yeah, I agree. Yeah, of course.
So most likely you are right about this electron in relating to the relativistic outflows, but for protons, I think we could not so easily exclude a large amount of acceleration of protons because of no observations, since just the target could be very low. I mean, that was, and therefore I understand for this system or supernova remnants, more or less we know the density. So otherwise, when talking about the hadronic part, we could have a certain conclusion if we know the density, target density.
No, but Felix, yeah, I fully agree that you may still, I mean, you have a lot of room to have quite a lot of luminosity in protons or nuclei in gamma ray binaries. You just don't see them because targets are in principle relatively low.
Yeah.
But the ratios here could be closer to 1 instead of, let's say, 1/100 or something like this.
Yes. Yes.
I think the challenge in this regard, and that's what Andre was on earlier, is really getting hadronic material into the pulsar winds. Principle, it's possible, but you really need to know the magnetic field structure that's happening around the interface.
Well, but can I reply to that? Because I think we were discussing this here in Barcelona some months ago. You have plenty of regions where you can accelerate particles, and beyond, let's say, the region where the shock is the strongest and more direct, you go outside the binary system where you form this kind of spiral structures. There you have plenty of instabilities growing. Even if you have strong magnetic fields, you very hardly avoid strong mixing at some distance at least. So another question is whether there you will have a strong acceleration. Maybe the acceleration is strongest inside the system. Who knows? But I mean, in principle, these systems are nice because the large density contrasts and this relativistic flows, they can easily lead to a strong mixing. I think loading is easy. I mean,
yeah, I mean, mixing will happen at some scale, but I was thinking you wanted to load where it's easy to tap into the energy, and that's easiest if you can really get into the wind.
Maybe. I'm not sure, because the point is that when you are outside the system, you have all this formation, the formation of this spiral structure due to orbital motion. And there you still can have quite a strong dissipation region. So maybe there you can still put protons into some acceleration process. I think Maxime
wants to chime in.
Okay, so Maxime, one quick question maybe, and then because we're getting close to 10:30.
Yes, maybe I'm wrong, but like, is it possible what if you will change your topology of a field, especially in a polar region, you can have much more toroidal field in this region. So your zone where you can efficiently accelerate particles will be smaller, and you unavoidably will need more efficient acceleration, and it can like be a smoking gun for understanding which mechanism is more preferable, leptonic or not.
Yeah, I mean, I have mixed opinions on this. I tend to think if you have a high alpha and Mach number shock, I don't think it matters the direction of the magnetic field. To be honest, we don't know at all what the magnetic field structure is going to be like in a binary. As I said, we were applying the assumption that a single star magnetic field type profile works, but this is a binary system with, I mean, a few 100-day period. This could easily be completely destroyed on large scales and be very, very turbulent. And in which case, then there's maybe no preferential field direction. And then basically, the only thing that's going to be really determined then is the global structure of the density, right? As you're sweeping up and accelerating particles, the shock velocity slowing down at different positions and different target.
I'm not sure what you will have so much disruption in this case. You have wind, which is faster than orbital motion. You have spiral expansion after alveolic surface. So it's quite predictable. So your poloidal zone can be much, much smaller.
Yeah, well, I haven't seen, I mean, I agree, but I think until somebody actually simulates it, it would be, yeah, you're sort of taking it on faith. I mean, this is what we did, but I think something might surprise. I mean, you can see that the density profile is quite non-uniform, and if you allowed for additional cooling and whatnot in the outflows, I mean, it makes a huge difference. If I go, I didn't really mention it here, but this is with cooling switched on, and this is with cooling switched off, and you can see that overall the entire density structure is quite different. And so the fields, okay, on this scale, maybe not so clear, but they certainly, when you get out into these regions here, they might start to see different field structures. Prove me wrong, Maxime.
That's good.
Wait.
Yeah. All right. We should be wrapping up. Just one more question to Brian. If you were to do a 3D IFC simulation, how would you pace the particle acceleration on? I mean, because we can't, right? What would you have? Like, you can get a nice 3D simulation, but how do you put in the particle acceleration details? What subgrid physics?
Yeah, so I mean, I think one can play around with this. I know what other people have done is some magic prescription for, well, not magic, prescription for injection efficiencies based on obliquity. This is largely motivated by some simulations. But generally speaking, we have a fairly good idea of what's happening at quasi-parallel shocks. We could simply, of course, always open to surprises, and I think clearly each observation brings new surprises. But I mean, you could play around with injection parameters. I would certainly be doing it as a first guess as a subgrid type model, because if you're on the MHD scales, you're way above gyro radius of any particle. So you're really just injecting particles with a prescribed power law and certain efficiency, and see how far you can get with that. Then you can start tweaking other parameters, like, again, obliquity dependence, normalization, and maybe we had a paper, I had it here in the backup slide, because people seem to forget that if you have weak scattering, you can get a whole range of spectral indices as well, depending on the magnetic obliquity.
Yeah.
So there's a lot of interesting physics here. In principle, yeah, it would be interesting to see how far one could push this with very high resolution simulations. I mean, people were doing impressive things already 15 years ago.
Yeah.
I mean, I think people should be ambitious and try to do something on top of this.
Okay. Sounds cool for the audience. All right. So it's past 10:30, so I think we need to wind down. So let's thank Ryan again, virtual claps. And I just want to remind you, there's going to be a talk in 2 weeks again on the pulsar gamma ray halos by Ryu. So please join us in 2 weeks, and let's thanks Brian for a great talk.